Hello everyone. We've covered quite a bit in our database programming course and are well on our way to becoming programming rock stars. I know your schedule is packed tighter than a SQL table with bad indexing, but today, for a few minutes, for a lot of minutes, we are diving into joins. Now, if you have ever stared at two tables and thought, how do I make these guys talk to each other? You are in the right place. So grab a coffee, get comfy, and let's make SQL joins feel less like a mysterious secret society and more like your favorite playlist. Because once you get it, you'll be mixing data like a pro. Let's go. Rarely in relational database development would you be able to satisfy the requirements of a query with data from a single table. In relational database design, during data modeling, you ensure that each business entity identified, including its attributes, describes one thing, which will translate in a retail business to having entities like customer, product, order, and order detail with their respective attributes. What this design implies is that to answer questions like what is our best selling product or who are our lowest purchasing customers, etc., we will need to combine data from more than a single table. For our best selling product question, we need data from the order detail entity, but the product name is in the product entity. This means our query will have to combine data from both the product and order detail entities to answer the question. Transact SQL provides a number of ways to combine data from more than one table. We will start with join. To discuss joins, let me introduce you to a very tiny database creatively named JoinDB. I will provide a script for you to create JoinDB in your local SQL server to follow along. You will see from the data model of JoinDB that the database is a scaled down model of a retail operation consisting of three tables or entities: buyers, produce, and sales. This model is strictly made to discuss joins in Transact SQL. In your career as programmers, you will often want to demonstrate and or troubleshoot a process. The more noise you can remove from your process so that you can step through it from beginning to end, the easier it will be for you to understand the process, and if you are troubleshooting, to find the root cause of the issue you are dealing with. You will hear the term minimum viable product, MVP, thrown around a lot as a software developer. Consider the MVP your model stripped of any distracting noise in order to understand or demonstrate and or troubleshoot a particular process. JoinDB is our MVP to discuss Transact SQL joins. Now that we have been introduced to our JoinDB model, we will return to discussing joins. As I have said above, joins are one of the ways to combine data from more than one table in Transact SQL. A join is an operation that allows you to query two or more tables to produce a result set that incorporates rows and columns from each table. You can join tables on any expression that is based on any column or combination of columns from both tables. Transact SQL supports three types of joins: the inner, outer, and cross joins. You can join more than two tables by using a series of join within a select statement, or you can join a table to itself by using a self join. To use joins effectively in Transact SQL, you need to use your knowledge of primary keys and foreign keys we discussed earlier in this course. Let us revisit the definitions of those keys. A primary key is one or more columns that uniquely identifies each row in a table, while a foreign key is one or more columns in a table that refer to a primary key in another table. Whenever you need to join two tables, the first thing you should decide is how the tables are related via primary foreign keys. Most times, these keys will have the same names in both tables, but this is not required. You will need to determine these relationship keys before you can proceed with writing your join query, because you will use the primary and foreign keys as join conditions. We said Transact-SQL supports the inner, outer, and cross joins. So let's start by discussing the inner join and look at some code examples in our MVP. The inner join combines tables by comparing values in columns that are common to both tables. These common columns majority of the time will have a primary foreign key relationship in both tables. SQL Server will return only rows that match the join conditions. The keyword here is match. The keys in both tables must match for the rows in question to qualify to be returned in the result set. All other rows where the join keys do not match are discarded. Before we zoom into inner joins, I would like to show you how the query engine evaluates tables when you use a join operation. What you see here is a logical in-memory representation of the three tables in JoinDB: produce, sales, and buyers in a join operation. Note how data in three separate tables are now placed side by side to form one logical table in memory, that is, join for further evaluation. Keep this picture in mind. We will return to it as we discuss the various joins supported by Transact-SQL. We said above that for inner joins, there must be a match of the join condition in both tables for the rows affected to be returned. What does that mean? Assume you were tasked to write a query that shows the buyers that have purchased a product in the JoinDB database. You are only interested in seeing the buyer's name and the quantity they purchased. A detailed design using the query designer reveals the following. 1. You need the buyer's name. This exists in the buyer's table. You need the quantity purchased. This exists in the sales table. You must use two tables to satisfy these query requirements, the buyers and sales tables. Checking the data model reveals that the buyer underscore ID foreign key in the sales table references the buyer underscore ID primary key in the buyers table. We thus have our common columns in both tables that we can use for our join condition. The final decision will be what type of join would we use. The requirement states we need buyers that have purchased a product. This means that for any buyer underscore ID in the buyers table, there must be a matching buyer underscore ID in the sales table. Our definition for inner join is that there must be a match of the join condition in both tables for the rows affected to be returned. This means the inner join will work for this query. We now have all the components necessary to write our query. First, you need the buyer's name, which exists in the buyer's table. You need the quantity purchased, which exists in the sales table. This means you are going to use two tables to satisfy this query requirements, which are the buyers and the sales table. The join condition is the buyer underscore ID in both the buyer and the sales table, and your join, the inner join. With these components, let's write the query to return all buyers that have purchased a product. But before we do that, let's look at that in-memory representation again. This time with just the two tables we are interested in, buyer and sales. Here you see the logical representation of a join between the sales and buyers table. We have said during our query design that the common column between both tables is the buyer underscore ID, which means we will be joining on the buyer underscore IDs of both tables. And because we are using an inner join, the data in the buyer underscore ID column of both the sales and buyers table must match. If you look at the first buyer underscore ID on the buyer table with a value of 2, this does not match with the corresponding buyer underscore ID on the sales table, which contains a null for that row. The number 2 is not equal to null, meaning it is not a match, and as far as an inner join is concerned, this row does not qualify to be returned in our query because we are using an inner join. The next buyer underscore ID on the buyers table with a value of 4 has a match with the corresponding buyer underscore ID on the sales table, which also has a data value of 4. This is a match. 4 equals 4. This means the inner join will return this row in the query. Going to the next row, we also see a match between the buyer underscore ID on the buyer table and its corresponding row on the sales table, both with a value of 1, which means this row will also be returned as we are using an inner join. The process of matching buyer underscore IDs in both tables will continue row after row, with matched row returned in the result set and unmatched row discarded until we run out of rows. A quick note on the row with a null for buyer underscore ID on both the buyers table and sales table. Do you think this is a match? That is, do you think the row with the null will be returned? We will find out when we finally write and execute our query, but for now, I will remind you of what we learned when we discussed null in an earlier topic. Null fails all equivalency. Now that you understand what goes on under the hood when you use the inner join, let's write the query so we can examine the inner join syntax. This is the syntax for writing an inner join. I want you to focus on the from clause. Based on our design, the first table is the buyer's table. So it follows the from clause. Then right below it, we issue the inner join command, which is where we introduce the second table, the sales table. The inner join is indented here as a visual cue that it is a continuation or dependent of the from clause that points at the source of data. Below the inner join and also indented, we have what we call the join condition. The join condition is also a predicate. Refer to our discussion of predicates when we discussed the where clause. In a predicate, the expression is evaluated and only values that evaluates to true is kept in the result set, with false values discarded. In joins, the join condition predicate is introduced with the on clause. Therefore, you have the on clause using the equal to comparison operator to check that the buyer underscore ID on the buyer's table is equal to the buyer underscore ID on the sales table. Notice that to identify which buyer underscore ID is which, we are using the dot notation. If you remember our discussion of the dot notation, we said whatever is to the right of the dot is contained within or a child of whatever is to the left of the dot. This means buyers.buyer underscore ID means that we are referring to the buyer underscore ID of the buyers table. And by the same token, sales.buyer underscore ID means that we are referring to the buyer underscore ID of the sales table. Also note that in the select statement, we are using the dot notation to make sure there is no ambiguity where those columns, buyer underscore name and QTY, are coming from. If we run this query, we will get 5 rows back, and if we compare our results set to the logical representation, we understand why those 5 rows make it into our result set. How about that null row I pointed out earlier? Well, it is not returned because, as we all know, one null does not equal another null. We see from the above the 5 buyer names that have purchased a product and the quantity purchased in the join DB database. The takeaways from this exercise are: 1. A good query design is inevitable. 2. Understanding that we need buyers who also exist in the sales table directed our choice of join, which is the inner join. 3. Understanding how inner join is evaluated logically is equally important. And finally, understanding how to write the join syntax with the inner join coming after the from clause and the on clause introducing the join condition is a must. All the other clauses and querying technique you've learned previously still works, even when you are combining data using joins on multiple tables. Therefore, you could filter the query we derived above to return only buyers that have purchased quantities greater than 30 units and sort the data returned in descending order. Pay close attention to the syntax now that we have added a filter and sorted our data. The where clause still comes after the from clause, and the other by clause comes after the where clause. Now run the query to see the 2 rows returned sorted by quantity in descending order. The inner join is the default join in SQL Server. This means that if you do not specify the type of join in your query and only write the keyword join, SQL Server will perform an inner join. Try running the query with just the word join used to verify it is still an inner join operation. Do not use null values as join condition. As we have seen previously, null fails all comparison. It is possible to chain joins together to write more complex queries. We will demonstrate this by adding the produce name to the earlier query requirement we started with. Now you are requested to write a query to return the buyer name, quantity, and produce name for data in the JoinDB database. Referencing the JoinDB data model one more time, our new design will be: 1. You need the buyer name. This exists in the buyers table. You will need the quantity purchased. This exists in the sales table. And now you need the produce name. This exists in the produce table. You must use those 3 tables to satisfy this new query requirements. That is, you have to use the buyers, the sales, and produce table. Your join column between the buyers and sales table is still the buyer underscore ID in both tables, and the join type still remains the inner join. To join the produce table to the mix, you will need to use the prod underscore ID primary key in the produce table and the prod underscore ID foreign key in the sales table, because these are the common columns between the produce and sales table. Finally, To qualify for this query, data in the produce table must be in the sales table, which means our join type has to be an inner join. Let's look at the in-memory representation of our new requirements before we write the query. You see here that we are adding produce data in the black font on a blue background to the inner join between the sales and buyers data we did earlier. From our design, we will be using another inner join between the sales table and the produce table based on their common prod_id columns. Because we are using an inner join, it means data must match in the common columns for the rows to be returned in the result set. All the prod_ids in both tables match except prod_id 4 in the produce table with a corresponding null in the sales table. Because 4 and null is not a match, we do not expect prod_id 4, whose produce name is bananas, to be in our final result. Let's write this query and see if we are correct. If you look at the new syntax, we have changed another inner join for the produce table to the earlier query. This new inner join has its own join condition between the prod_id in the sales table and the prod_id in the produce table. Then we have added the prod_name column from the produce table to the select list to display the produce name. Run the query to review the newly added produce name and note that indeed bananas is not in the list, and you know why. The next type of join we will discuss are the outer joins. There are three types of outer joins, which are left outer join, or left join for short, right outer join, or right join for short, and full outer join, or full join for short. With outer joins, you can request to preserve all rows from one or both sides of the join, regardless of a match or not on the other side of the join based on the on predicate. For the left outer join or left join, all the data from the table on the left side of the join is preserved in the result set. This means all the data from the left table is returned. The left join does what an inner join will do, that is, return all matching rows, but it would also return all rows without a match in the other table, with nulls used as placeholders in the right side. Let's see a query that uses a left join between the buyers and sales table. You will see that the syntax is almost like the inner join, except here we are specifying left join. We could have also written left outer join, but we will stick with the shorthand left join to join the sales table. With this syntax, the buyers table is the table on the left, and the sales table is the table on the right side of the join. The join condition as specified in the on clause is the buyer_id from both tables. We said in a left join, data in the table on the left side of the join is preserved, and all unmatched rows on the right side of the join are also returned with nulls as placeholders for those unmatched rows. Also note that we are displaying all the columns in both tables because of the asterisks in the select clause. For our narrow tables, that's fine, but always specify the columns you need in the select list. Run the query so we can review the data returned. The data returned shows that the buyers table is now joined to the sales table with a left join. Buyer_id 1 in the left table the buyers table, has a match in the right table, the sales table, and is therefore returned. Same for buyers underscore ID 3 and 4 in both tables. Buyer underscore ID 2 on the left table is also returned, although there is no corresponding match for that buyer underscore ID in the sales table. You see, however, that a null has been placed in that row in the right table where a match wasn't found. If this were an inner join, the row with buyer underscore ID 2 will not be returned in the result set because the inner join only returns matched row based on the join condition. The right outer join, or right join for short, preserves the data from the table on the right side and based on the join condition will return matching rows on the left side, including non-matching rows with nulls as placeholders. I have rewritten the query above using a right join. Note how I have swapped the tables with the buyers table now the right table and the sales table the left table. The join type is now a right join specified by the right join before the buyers table. We could have also written the right join as right outer join. Running the query above shows that the table on the right, the buyers table, has all its data preserved. Where matches exist with the left table, the data is returned. But where there is no match in the left table based on the on condition, a null placeholder is used. For the full outer join, or full join for short, data from both sides of the join is preserved. Based on the join condition, matched data is returned. Also, rows on the left with no match on the right will have null placeholders on the right, and rows from the right that has no match on the left will have null placeholders on the left. Let's review an example of the full join to discuss its syntax. The syntax is not different from what we have seen previously. Note the full join used to specify the type of join and the on clause specifying the join condition. Run the query. Note that based on the prod underscore ID join condition, data from both tables are preserved with matches returned. There is, however, a prod underscore ID in the produce table, prod underscore ID 4, that doesn't have a match in the sales table. And you see null placeholders representing that non-match. All the rows in the sales table are matched in the produce table, which is why there is no null placeholder on the right side or produce table side. If there were, the full join will display this as well. What we see here makes sense from a business perspective because we do not expect to have sold products that we don't currently have in inventory. Now, let's make things interesting by writing a multi-join of 3 tables using full joins. The query shows a multi-join operation made up of 2 full joins. Take some time to make sure you understand that this query is joining 3 tables using full joins. The first full join is between the buyers table and sales table, with the join condition being the buyer underscore ID in both tables. The second full join is between the sales table and the produce table, with the join condition of this join being the prod underscore ID common on the sales and produce tables. When you run this query, you see that apart from preserving data in the pair of tables joined as dictated by the full join, you see that one buyer, Sean Chai, has not purchased any produce from JoinDB as shown by the null placeholders in both the sales and produce section of the results set. We may want to check up on Sean to know what's happening. Also, one produce, bananas, has not been sold to any buyer as nulls in those sections of the results set shows. Maybe we may want to rethink carrying bananas in our inventory or come up with some marketing plans to gin up bananas enthusiasm. This would be a good segue to an important use of outer joins. As I've teed up above, the outer joins can be used to answer questions like which buyer or buyers have not purchased a product on our inventory, or which product has not been sold, etc. We can see that in both cases, if we query the tables using outer joins, the answer to those questions will be the one with a null placeholder in the join condition column of the order table. Let us use a left join to answer the question which buyer or buyers has not purchased any of our produce in the JoinDB database. Run the above query we wrote for the left join to refresh your mind on how the data will look like with a left join. As I said above, the answer to the question which buyer or buyers has not purchased a produce from JoinDB will be the one with a null placeholder in the join condition column of the order table. You see the null placeholder in the buyer underscore ID column of the sales table. Therefore, if we filter non-null values in the sales table, we will get the answer to our query. Our final query contains a filter with the predicate returning row with null buyer underscore ID in the sales table. Note that we are looking at the sales table for a null buyer underscore ID. If you run this query, you will see that Sean Chai has not purchased any item from JoinDB. I have returned columns in the sales table for clarity in this demonstration. Displaying null columns won't be required in real-life situations. See if you can write a query to return the products or products that have not been sold in JoinDB. For the outer joins, left outer join, right outer join, and full outer join, you see that all the data in one table is preserved with the matching rows with the other table based on the join condition returned and the non-matching rows replaced by null placeholders in the case of the left and right outer joins. In the full outer join, data from both sides of the join are preserved, and based on the join condition, matching data is returned and non-matching data on both sides are returned as nulls. With this type of joins, deduction about data not available on the other side of the join operations can be made as we have seen above. The final type of joins supported by SQL Server is the cross join. The cross join returns the Cartesian product of the tables in the join operation. What this means is that if you have table A with m number of rows and table B with n number of rows, a cross join between tables A and B will yield m multiplied by n number of rows. So if table A contains 5 rows and table B contains 4 rows, a cross join between tables A and B will be 5 multiplied by 4 rows, which yields 20 rows. Cross joins display every possible combination of rows in the joined tables. Let's look at a syntax of a cross join between the buyers and sales tables of join DB. From the syntax above, you see the cross join clause used to join the two tables concerned. Because you are looking at every possible combination of rows, a join condition is not required for a cross join. If you run this query, you will get a result set of 20 rows. This is because the buyers table contains 4 rows, while the sales table contains 5 rows, the Cartesian product of which results in the 20 rows in the result set. There is a special type of join we need to look at before we leave the topic of joins. But before we do that, we need to discuss the concept of table aliasing. We have seen column aliasing, where we replace the name of the column with another name using the as keyword, as seen in the query here, where we are replacing the QTY column with an alias quantity using the as keyword. Well, we could alias table names as well. If you look at the query above, you see that we are referencing the tables with their fully qualified names in the from and join clauses, which means when we write the on clause, we use the table name dot column name, and in the select clause, we also use the table name dot column name in dot notation. Now let's alias our table names. You see from the new version of the query, in the from and inner join clause, we have alias our buyer table as B and our sales table as S, respectively, using the as keyword. The result of this table name aliasing is that wherever in the query the buyers and sales tables are referenced, they are now B and S respectively. Therefore, in the on clause, it is now b.buyer_id equals s.buyer_id. In the select clause, it's now b.buyer_name and s.qty as quantity. And finally, in the where clause, it is now s.qty greater than 30, showing that our table names are now referenced by their aliases. If you run the query, it will return the same number of rows as the first version did. Apart from the special type of join we will discuss next, table aliasing, in my opinion, is a matter of personal preference. While some make the argument that table aliasing helps with writing compact code, I would argue that they detract from code readability, especially when the alias used is not descriptive. Therefore, I will leave the choice to alias or not to alias your table names to your discretion. For this special type of join I've been teasing you with all day, it is called the self join. It is a special instance of all the types of join we have discussed above. And you are right in guessing that based on the name self join, you are actually joining a table to itself. You can use self joins to find rows that have values in common with other rows in the same table. Because you are dealing with a single table and joining it to itself, you must specify different table aliases to reference the two copies of the same table. This is an instance where table aliasing is mandatory. We will look at self-join with an example. Suppose you were tasked with displaying a pair of buyer IDs, that is, two buyer IDs that have purchased the same product in Join DB. Below are the columns expected from your query. Designing this query reveals sales data containing buyer underscore IDs and prod underscore IDs are in the sales table. To get two buyer underscore IDs side by side, we need to join the sales table to itself, that is, self-join. Because you are looking at buyers purchasing the same product, the join condition is the prod underscore ID. To ensure we are not dealing with duplicates or mirrors, the buyer underscore ID in one sales instance must be different from the buyer underscore ID on the other sales instance. Based on the first step in our design, we know we will be working with the sales table. The second step requires us to join the sales table to itself using a self-join. Let's do that. As you can see here, that a self-join, as we have said earlier, is a special instance of joins in which we join a table to itself. As a result, you see here that we are joining the sales table to itself using an inner join and appropriately aliasing both sales table as S1 and S2 respectively. Look at the on clause. We are joining both instances of the sales table based on where their prod underscore IDs are equal to pull those buyers purchasing the same product. While this is not our final query, run the version of the query you have here. You can see both instances of the sales table in a self-join. From this data set, we can pick our required columns to display based on the query requirements above. We will display s1.buyer underscore ID, s2.buyer underscore ID. Either s1 or s2.prod underscore ID will suffice because they will both be the same. See the data value. So I will pick s1.prod underscore ID. Let's display these columns in our select list. Now I am displaying the required columns, and to differentiate them, I have aliased them as buyer underscore 1 and buyer underscore 2. You can run the code you have here to view your data while we proceed to the final step in our design. Design step number 4 requires us to remove duplicates or mirrors. This simply means we must only return rows where buyer underscore ID 1 and buyer underscore ID 2 are not the same. This is a filter operation, so we need our where clause. A good trick to ensure buyer underscore 1 and buyer underscore 2 are not the same is to assume one will be greater than the other. So let's use this as our predicate, giving us the new query. Using this trick in the where clause ensures that data in buyer underscore 1 and buyer underscore 2 column will not be the same or mirrors of each other. When you run the final query, you will realize that buyer underscore ID 4 and buyer underscore ID 1 have both purchased the same produce, prod underscore ID 2. Remember, in a self-join, you are performing any type of join but on the same table. As such, table aliasing is mandatory. As an exercise, extend the query above by returning the buyer's name and common produce name. Your result set should have the following columns. Once you are done with that, try your hands on this other exercise. Using the employees table of the NotWin database, Write a query to return the following columns: employee ID, last name, first name, title, and the manager's last name. Note that the report to column of the employees table is the employee ID of that employee's manager. Joins are important operations in relational databases because you will need a way of stitching back comprehensive information that are in different entities of your data model. Think of inner joins as best friends who share everything, left joins as one-sided friendship, right joins as the flip side of that, full joins as an all-inclusive party, and cross joins, well, those are just chaotic social mixers. Nobody wants to type out long table names all day, so use table aliasing, but use responsibly. And finally, self-join. Let's face it, sometimes you just have to work with yourself. Keep practicing exercises that will reinforce your understanding of all the different types of join. See you in the next class. Thank you.